Good morning, good day, wherever you may be. We have got another exciting session today, and I hope you're all awake, and I hope you're going to see the window. I'm just going to go back to my live chat, so I'll be able to see what you're saying. Just 1 second. So I wrote there, I hope you can see this all ready to start soon. And you should be able to see at the moment the screen of the observatory. And that is a live view, of course, not this beautiful picture that's taken in the afternoon, but let's have a quick look at what the telescopes look like right at this moment. And you can see there is the time indeed, so it's 1 day later in Australia, and you can see we've got a lot of moon. That's why it's so illuminated. There's a lot of moon, but still we can do a lot with this. We can do a lot. And do I have something exciting today for you to follow? So let's go right back to the launch pad. And this is what our live launch pad looks like. You can see here to the right, if you look at the map, let me just get my arrow quickly to show you what I'm... So we're pointing at the same thing. There we go. That's a nice arrow. That's where Australia is. 1 second. There we go. And you can see it's nighttime there. And indeed we have a daytime everywhere else. And you can see on the live screen preview here that there is a lot of moon. But it's not going to worry us at all. And do I have some exciting things today? And I'm just dying to show you. So again, for those who have not seen our wonderful iTelescope observatory in Australia, this is what it looks like. Okay, during the day, you have this beautiful panoramic view of the mountains, and you can see really virtually for tens, if not 100 miles and on. And below that, you can see we've got many telescopes there, and we're going to use 1 or 2 of them now. And today, we're going to go and explore something quite incredible. So, our first target is going to be the Black Eye Galaxy. The Black Eye Galaxy is in the constellation of Coma Berenices, and it's very, very far. It's 19 million light years away. We're really traveling far. So what it means is what we're actually seeing has happened 19 million years ago. So the light takes a long time to reach us. And it's quite distant. Yes, it's quite distant. And there is so much to say about this because this is the most peculiar galaxy that we know, and we don't know of any other one that exists. At least we can't resolve it with telescopes. So what is so incredible about this galaxy? Well, let me first a quick overview of where it is. This is always the beautiful southern sky that I took. This pointing the arrow right here is about looking south. Okay, there's the Milky Way just rising in August when I was there, and then we are pointing into this direction and further, which is not on my photograph, but over there is the constellation of Coma Berenices, and that is where the Black Eye Galaxy is. And it's very, very well visible from the northern hemisphere, very, very, very well visible. So that's why we're going northwest there with our telescopes. So without further ado, let's take a look and let's switch over to our live view. There we go. Let me get rid of the arrow. There we go. So that is our live view. You can see, let me just jump into the telescopes here. There we go. And I've already got, let me see if this is correct. Yes. This galaxy is also known as Messier Object 64, which means you can see it from Paris, because there was a famous comet hunter and he didn't like these annoying objects other than his comets, and he named them after Messier, and this is M64, so very visible from the northern hemisphere. But I have already launched our big telescope T27, that's a plane wave telescope. By the way, if you do want to chat, you're very, very welcome to just jump in and chat, okay? I'm here to answer your questions. I'm very delighted to see your comments. I'm looking at the live chat screen. I'm just going to type something in and say hi. Let's just try this. There we go. And let's see now if I can get my screen back so I can see your comments just in case they come in. Yes, okay, very well. So I can see your comments. If you have any comments, any questions, don't hesitate. I want this to be highly interactive. That's what we are doing here at iTelescope. We want you to really, really enjoy the session. So let's get going. So this galaxy, and let's have a preview now. I've already launched the telescope, so I'm going to give you a live preview now. And here it is. It's absolutely marvelous. Now you can see this looks really, really peculiar. It looks more like a science fiction movie indeed. And you can see there is some influence of the moon, but it doesn't matter. It really doesn't matter. The structure of this galaxy is coming out incredibly well. And this is with our telescope T27, just as I'm running. That's the last image that I've just got live. So what is so interesting about this? Well, first of all, let me get my wonderful arrow here so I can really show you what's going on here. There we go. There's my arrow. The width of this galaxy, so it's at a distance again at 19 million light years. Really, really far. So the light has taken 19 million years to reach us. So today, if you were on that galaxy somewhere in a system, who knows if there's life out there, they would experience it very, very different. So the outer radius is about 40,000 light years, so it's smaller than our own. We have a diameter of about 100,000 light years in our own galaxy. And now comes the interesting thing, it really looks peculiar. It really, really looks peculiar. And even with a single image, we can see that something strange is going on. Look at the inner part of this galaxy where I'm pointing to now. I'm going to try and see if I can magnify this a bit more. Oh, not the arrow. Sorry, 1 second. Let's see if I can instead magnify the image a bit. That's what I'm looking for. 1 second, not my arrow. Let's get rid of my arrow and see if I can. Yes, that's it. Let's magnify this a bit in the screen. That's much better. And let's do a little bit more magnification. So this is the live image. All we did is we took a 5-minute image and we can see quite a lot on this. It's quite marvelous actually. So let me get my big arrow that has become far too big. Just make it a bit smaller. There we go. That's much better. That's much better. So, so you can see something weird is going on at the center, and that is correct. So what they found out in 1990s, and I actually started reading the original paper from the astronomers, they're really, really exciting. They found out that the outer part, the inner part, is rotating in the opposite direction of the outer gas cloud. Now that is incredible. That is an incredible discovery. So outside, it's like being on a merry-go-round, and the inner merry-go-round is going in one direction, the other one's going the counter direction. Now the question is, what is going counter to the other? That is the question. So what they found was all the stars are rotating at the same direction as the inner circle. Okay, so this is quite incredible. And so that's really, really peculiar. Right? That's really, really peculiar. So what has happened there? How is it possible? Galaxies usually rotate around the center, their core, in one single direction. And this seems to have an outer dust cloud that is of almost the same mass, the same weight, rotating in the opposite direction. Really, really weird. So they started looking into this closer and said, well, the first thing you would think of course, there can be two galaxies that may be colliding with each other. That is an obvious thought. So, and then somehow you would have an outer part that rotates in the opposite direction, but that didn't fit the model at all, because you would get a very, very disturbed galaxy. If you remember, when we looked at M83, yes, it was M83 last time, and you can go back to I think that was the first episode, you can see that the inner part of the core of the galaxy looked much larger, and there was an off-center there. So you would expect merging of galaxies to happen in very, very weird, disturbed ways. A very, very disturbed galaxy, by the way, is called Centaurus A, wonderful object, and we will also cover that in our, in our next series. It's really, really incredible. But this is very different. So they looked at this, and they started measuring dust, the dust clouds. They resolved it with the Hubble telescope in incredible detail, and they started studying the velocity of different dust clouds. And they came to the conclusion that this must have been a dwarf galaxy swallowed by a large galaxy. Okay, a dwarf galaxy is a small galaxy such as the Magellanian clouds that we have rotating, those satellite galaxies that are rotating. You can beautifully see them from the southern sky. Just seen there. Let me get my arrow and let's hope it's not going to crash now. But that is the Magellanian Cloud, okay? And that is a satellite galaxy to our own Milky Way, okay? And so what is believed, let me just go back to our live image here. What is believed is that the outer dust cloud is indeed from a dwarf galaxy that was swallowed up. And there is so much dust here. It's just incredible. I always ask myself, what would it look like if we were somewhere in this strange galaxy? And we probably, if we look up at the Milky Way, we have these very dark patches, which comes from the dust clouds. And these dust clouds are star formation areas that are very important, together with the bright, shining young stars. Those are formation centers for new stars, right? So, but if you were now on the Black Eye galaxy, I think we would see a lot of dust. A lot of dust. If we were standing there looking inwards, this would just be incredibly much dust. It would look completely different to our Milky Way. Now, this is speculation, right? This is speculation. However, there's good reason. This is another beautiful picture that was taken by Josep Drudis. Again, thanks to him. I'll put the reference to his website down, but he has taken a much more detailed image here, a color image, and you can see, indeed, if you look inside, you can see that there is a lot of dust even around the central halo. Okay, looks very, very different to anything we've ever seen, and that's why they called it this thing the evil eye. Also, the evil eye, very, very different. Okay, so when looking more at some science here, they found out, and that's very interesting. A lot of the dust here tells us very, very much about the structure and evolution of a galaxy. And they found out that a lot of dust has what we call photoluminescence. That's a word, photoluminescence. Now, what does photoluminescence mean? It means, photo means light, and it's something is being excited by light. So what happens here is that ultraviolet light from young stars, or from the center of the galaxy, from wherever, from all the star regions, from the stars, are coming and exciting the dust, and the dust is absorbing this and re-emitting it in the visible somewhere. We call this photoluminescence, okay? So it's conversion from a short wavelength to a longer wavelength, okay? Luminescence, fluorescence are terms you may have heard of. And that happens very much, and by looking at the longer waves, that's more the red waves, okay, the far red, they learn a lot about the dust structure. But now comes the interesting thing. I read this paper, and they said they found a lot of material. They suspect carbon, silicon, and all kinds of different clusters in those, but really none seems to so far match the observations. So they do models, because nobody can go up there to this galaxy and say, hey, this is what it looks like. We can't take a sample. So science is a lot of guesswork, and this is also how I did my PhD. It's a lot of guesswork. You don't know what's going on anywhere, so you make certain assumptions, and you hope that somehow you can make some experimental evidence here on Earth, because the science on Earth is very similar to up there. But the models don't seem to really fit that of interstellar dust. So there's a lot to be researched still, because you have to assume certain things and then you model, and then you can see if your experimental results are the same. Well, they're not. So in short, this galaxy is still a big mystery. Once again, you have the inner rotation rotating at the same speed as the stars, and then the outer having a counter rotation. Really curious object. And then of course you have this incredible image. I took this here with the gave credit here to the Hubble image heritage, but I have to show you this image because you can see the incredible details here of the black eye galaxy. Of course, we cannot resolve these things with our own telescopes, although I think we're doing very, very well. But you can really see these star-forming regions in these incredibly thick dust clouds. Okay, so quite an exciting and mysterious object. So before we go on, I will give you one last look at at this 5-minute view. And what I'm doing is I'm stacking this, and these images will be available. So much for the black eye galaxy that is 19 million light years away. Okay, so let's jump to the next and final object. I don't want to make it too long today because I think last time was a little bit too long. So our second object, let me just jump back to the launch pad and get rid of my arrow again, is also exciting. Okay, so we are now going to, one second, I just have to put my, I think this is going a little bit too loud here, what I'm hearing. 1 second, so just excuse me for a second. Okay, let's see, where is telescope 27? What are we doing here? No, that's the wrong telescope, sorry. Telescope 30 is the one that I was looking for. Yes, this is very interesting. Now we are going to go somewhere completely different. Sorry, let me just give you a live, I'm giving you the wrong image here. 1 second. Oh, I know what's going on. I have I have scaled this up so you can see it. That's why you're not seeing it. Sorry about that. There you go. There you go. I was increasing the magnification so much. Oh, there's Josep. Hi, Christian. Josep here. Thanks for showing my picture. Yes, the M64 was taken with an 11-inch. Okay, that's right. The galaxy is one of my favorites. So this is Josep Astro. Wonderful he's here. Josep is one of the most incredible imagers who's just given the comment in of this beautiful M64. So it's also his favorite. So obviously, I mean, Josep is not only an incredible imager, but he's also an incredible scientist. He's a good friend of mine, and we do a lot of science together. And he gets all the credit for this beautiful image of M64. So it's also his favorite, and it's the most mysterious, one of the most mysterious galaxies that we know. Thank you, Joseph. That is great. So now we're going to go somewhere completely different. And this is quite exciting. So the next object, let me just get this back on. There we go. Here we go. There we go. We are now going to what we call a planetary nebula. And this is called the Eight-Burst Nebula in the constellation of Vela. And it's very, very close by. Okay, so I'm going to explain to you in a second what planetary nebulas are, but let's first see what the result is. Okay, so I'm just going to jump back to our live screen and then I will explain. So let me see if I get a preview of the last image, because I've been running all these telescopes in parallel. This is all live, okay? So let's just see if I can get a preview here. It may take a minute or so. Sometimes the refreshing rate takes a bit of time. But I'll explain to you what we're going to see. So what is a planetary nebula? Well, a planetary nebula is a word that is completely misleading. Whoops, yeah, there it's coming. There's an image coming. Let's see what it's going to look like. So just building up the image. Beautiful, beautiful, beautiful. Let me just zoom in. Let me just zoom in. Really try and zoom in as much as possible. This is quite incredible. Not bad for a 5-minute picture. That's quite remarkable, actually. So I'm going to zoom in even further. 1 second. I'm going to zoom in to about 800%. So we can have even a better look at this. Now let me see. Here it is. Here it is. Very nice. Beautiful. So this is this is actually quite remarkable. What I did here is I knew what the result was going to look like. I've played a little bit with filters before because, first of all, let's start from the beginning. What we're looking here is called the Eight-Burst Nebula, and its appearance is called Eight-Burst because when you look through small telescopes, it looks a little bit like an 8. Now, I can't see an 8 here, but if you look carefully, and I'm going to just point an arrow here, you can see here that there's actually a second sort of a planetary nebula behind that, okay? And what is actually a planetary nebula? So it has nothing to do with planets. It was a word that came long ago when they were looking at Venus and others, and they sort of thought, well, those must be distant planets, so they called it planetary nebula. Nowadays we know that it actually is the dying stage of a star. A star that is, this is very possible that our own sun is going to look like this one day. In fact, stars that have a mass of 8 times that of the sun or less are likely to going to end like this, okay? And what happens towards the end of the life of a star, and don't worry, our own sun is going to have a couple of billion years still, but one day it'll have a similar fate. We know that now by looking at all these distant stars in our own galaxy, by the way, because this is 2,000 light years away. So this happened 2,000 years ago. And by the way, this could be long enough. If we would probably be standing right next to it, it may not even be there anymore because they have a very, very short life. There are only a couple of hundreds of such planetary nebulas in our own galaxies and a galaxy. And if you think about it, we have about 100 billion stars, so that means that their life is very, very short. They occur all the time because stars live and die. And it just, at the moment, the time scale, when we look at our Milky Way, there are only about 100, 200, 300, 400, about 500 such planetary nebulas. So what happens was, as at the end of the life of a star, when there's no more hydrogen to burn, the gravitation just gives in. Okay, or how should I say, the force of fusion just gives in, the radiation pressure, and the star completely collapses by gravitation. And by doing so, a lot of mass just leaves the star in a big burst, and this is what causes this planetary nebula. It then becomes a red giant, and later it becomes what we call a white dwarf. That's the ultimate fate, okay? So this collapse allows the inner core of the star to radiate strongly, causing the outward moving cocoon of gas to glow brightly, yes. So the inner part, and I'll explain to you exactly what we're seeing here. You can see a bright star in the middle, but it's a little bit misleading. But for now, usually planetary nebula have a bright star in the middle that is really bringing this nebula to glow. Now, on a large scale, before I go to large scale, let me just show you how different this looks at different wavelengths. So this was taken with a sulfur. This I took with a sulfur. I've got some more questions here. Hi, all came to my mind, all those raw images from space telescopes publicly available. Yes, Sammy. Sorry, I just saw your comment. Yes, they are. They are publicly available. So the space telescopes, all the Hubble sites are publicly available. You just have to Google them. Okay. So that's true. And then Bo says, is some kind of virtual telescope we can use online at our disposal. We can do it at our site, sort of Google Earth capabilities. Right, there are virtual telescopes available, and there are quite a few. If you have Microsoft, there is there's a virtual telescope that they use, and the name doesn't come to me. But all you have to do is for Microsoft, I think it's called Virtual Telescope, and there's another one that Google has, and it's called Sky something. I don't have it, but both Google and Microsoft have online virtual telescopes, and it's wonderful to do that tour actually. So you're right, this does exist. So you can have a virtual, beautiful tour of the universe. You can. I hope that answers your question. So yes, both Google and Microsoft have such tools available. That's So much for the and I do use both actually. I do use both because it helps prepare my, my own schedule. So good question. Thank you. Okay. So yes, the space telescopes, Sami, are also available. Everything is available, right? So now what we did, let's jump back to the emission nebula. Emission nebula are very different. Emission nebula are not like when you look into your fire. Okay, your fire has all the different colors. Emission nebula are basically caused by the excitation of a very intense star. In this case, it would be a white dwarf that has collapsed, is really shining, and it's like an amazing death of a star. Illuminating and exciting its own nebula. And what happens there is it's mainly hydrogen that gets excited. So we're looking at sulfur here. And what is interesting, these are the sulfur lines. So this is ionized sulfur, okay? Sulfur can be ionized twice, it can be ionized 3 times, once, and so on. It depends on how many electrons are kicked out. And what happens is that you see this incredible structure. In this case, you can see the sulfur is very prominent as a ring, and in the middle you can see a star. But what happens if you, for example, look at hydrogen and oxygen? It looks very different, okay? A hydrogen, you can see the hydrogen density of that planetary nebula looks completely different. I just took that about an hour ago. So you can go through, look at hydrogen, oxygen, and sulfur comes out nicest. You never know what it's going to look like because the spectra of different planetary nebula look very different. And then when you superimpose these, you get these beautiful images, okay? That's what it's all about. But let me tell you a little bit more now about planetary nebula because they are absolutely exciting objects. This is the stardust that you and I are also made of. This is the death of a star. It's bursting its particles out into the universe, and somewhere it's collected. Maybe new planetary systems are developed that way. They are sucked up by other galaxies. They are sucked up into new interstellar dust and so on. A completely new cycle starts that way. Oh, I got lots more questions here. Sorry, 1 second. Let me see. Google Sky. Yes, that's right. As Dr. says, yes, they are. That's right. I'm just seeing the comments. Thank you, Josep, and thank you, Clayton, for clarifying that. I'm just seeing your comments here. Good. Okay, great. Now, so what is so exciting about these planetary nebula? Well, that's the death of a star. So you can ask yourself as a scientist. This is always the interesting question: is how dense are these? How much does the star actually lose? Do we know anything about this? And the answer is yes. And the first thing that may completely surprise you when you look at this planetary nebula, is that actually, you would think, wow, this must be a massive emission nebula. If I was standing in the middle, I would completely glow to pieces, right? Because it must look so hot. And it is very hot. Okay, it's typical star temperatures are multiples of our own sun. Okay, you're talking about 20, 50,000 degrees, sometimes even more. Okay, huge temperatures, right? And so the question is, how dense are they? How much material is a star losing? And it's beautiful. I just want to explain to you how scientists actually understand all this, how they do this. And what they do is, with the Hubble telescope, with large telescopes, they are able, and I'm going to show you now a picture here, again of the Hubble telescope. Okay, this is a beautiful, beautiful image. But I need to explain to you what scientists learn from this. Okay, so you can see all the different colors. First of all, the colors tell you a lot. The blue ones typically come from helium, they come from oxygen, and so on. The redder ones come more from sulfur. The reddish ones come more from sulfur and from hydrogen alpha and so on. So it's a mixture of all these colors that tells you something about the temperature. And it tells you something about the temperature of the star in the background. Now, the curious thing about this nebula here, you see this very, very bright, and I'm going to increase the scale. Oops, no, not my arrow. Wait a second. I'm going to increase the scale for you because I want to... Wait a second, that's also not the correct one. 1 second, I want this one here. I want to increase the scale for you so we can take a closer look. Now, this is quite remarkable. Here we go. What you find here is there's a bright star, And you think the bright star is the culprit. That must be the white dwarf. But it's not. It is a magnitude 16, which is quite dim. And that is the star that is actually responsible, that kicked out this huge nebula. So there just happened to be another star in the way here. And that's what's causing this very, very strange looking figure of 8 or so, because both these stars have contributed to illuminating this emission nebula that is caused by this very, very small dim star that you can see there. Okay, so that's where it comes from. That's where it comes from. Now let me zoom out a little bit again. Get this right here so we can go back to the normal scale. Let's just see if we can get this. Not sure if I can do this at the moment. 1 second. Let's just see. Well, you know what? That's okay. I'm going to go and jump back to my other image. Let me see. Where is it? Here. There it is. There it is. That is the image. That is the image that we were looking before at of the planetary nebula. So my question was, how do we learn things about the planetary nebula? And what scientists do is, I just showed you this big Hubble telescope picture, right? This one. And they can dissect the image and look at different cross sections. And then what they do, and everything in science is based on ratios. It's just like doing maths. How much sunshine do we have today and how much clouds? How dark is it? And so on. So they take ratios. So what they do is they take ratios of the sulfur emission lines, okay? The sulfur emission lines. And what we saw here, if you talk about sulfur, this is the sulfur emission line that we just took live with the telescope. So they would be dissecting this image very carefully and saying, okay, let's see what the one sulfur line to the other does. And then we do all the experiments on Earth and we make models. And by doing that, you can calculate the density of the gas. That's the main thing. So by looking at the different ratio of sulfur lines, you say sulfur, the one sulfur line and there's another sulfur line, you look at the different ratios and you find out that there is a dependence on density. So the ratio varies and it has to do with the so-called forbidden lines, and I won't go into forbidden lines, it gets too much science here, but by looking at the ratio they can conclude the density. And now comes the exciting thing. I was asking, if you would be standing in the middle of this, what would you notice? And the answer is nothing. Nothing, nothing, nothing. And why? Because you can calculate the density from all this, and the density is better than a vacuum that we have. These particles already look marvelous on a light year scale. But if you're standing in the middle, you'll feel absolutely nothing. Nothing. You're talking about 1,000 particles per cubic centimeter. Okay? Now you'd say 1,000 is much. No, it's not. It's very little. It's 1,000 particles per cubic centimeter is less than the best vacuum we have on Earth. So this is an incredible conclusion, actually. So the density is very, very low, and that means that up there, the physics can be very different to what we experience here on Earth, and that's why at first they thought they're discovering new materials up there, which they were not. These so-called forbidden lines were just very, very unlikely to occur on Earth because they can only occur when there is almost like a vacuum where atoms don't collide with each other. So that's the interesting thing. And then I just did a quick estimate on this nebula. What I did is I looked at the size of this nebula, and it is about, let me just look at my notes here, what the cross-section was. I think it was, yes, about 0.4 light years. And from that, if you know the size, you can calculate the volume of particles, how heavy they are, and there's mainly hydrogen in there. So if you do all this calculation, you can actually calculate how much was emitted by the star initially, and I estimated it must have been a few percent only. So a few percent is actually this incredible incredible starburst. It's not a supernova. Supernova occurs only with heavy stars, but a planetary nebula is when the star starts collapsing, it ejects a lot of mass to find a rebalance. Okay, it's like a rebound, and this ejection is a couple of percent that has gone out there. Okay, so this is what we learn from planetary nebula. So it's quite a lot. We can learn a lot about the star in the background. We can learn a lot about how hot it is. We can learn what the composition of the star is. We can learn all these things. So planetary nebula are very, very important to understand. But that's not all. There's one final thing that one can also learn from planetary nebula. That's quite exciting. Sometimes, I mean, you know that in the evening and during the day, the sky is blue. And at night, the sky is red. And the reason for that, and we had that already in the first episode, is they are very, very fine aerosols. Aerosols, mainly nitrogen with oxygen. And they cause light scattering. These particles are much, much smaller than the wavelength of light. And that means, and one can show that blue light is scattered far more than red light. So what it means is, this light, as it travels through our own Milky Way, sometimes hits interstellar dust. And interstellar dust also consists of incredibly small particles very often, and they scatter light. So actually what comes out from these planetary nebula sometimes, not in this case we have a straight view, is it looks much more red than it should, right? Because the blue light is scattered out. And by looking again at the ratio, science is all about looking at ratios. So they look at the ratios of some lines that have shorter wavelengths to the emission lines that have longer wavelengths, and the emission lines with longer wavelengths travel all the way to us. And by looking at the ratio, they can actually estimate how much dust is between us and the planetary nebula. So quite fantastic, the amount of science that you can do with these planetary nebula. And that it concludes my session for today. I hope you found that exciting, my friends. Maybe a lot of science, but you can see science is very, very exciting. I will make these beautiful images available. And again, thanks to all of you for joining. Maybe a lot of explanations today, but it's just amazing what one can conclude by just looking at light. That is the main thing. So having said that, I wish you all the best. If there are any more questions, and thank you for participating, Sami, I can see Clayton here, Bo, of course my friend Josep was there. Thank you for being there, and I will be on holidays. Very interesting, thank you for your comments, thanks Joseph, thank you. My rain meter, that's an interesting, my rain meter OC, thank you. Well, it was marvelous, I really enjoyed showing you this, and thank you for your participation. I am going to be for 2 weeks now on holiday, and when I come back in March, we've got lots more interesting stuff to explore together. So I'm looking forward to that. I will also be going to Australia. I'm just finding the time, and I'll do some live shows from there, because some things you just better not do remotely when they're interesting, and you may have to stand next to the telescope. So I will also do that. Thanks, Sami. Thanks. Very interesting. Happy springtime, and all the best to you, my friends.